So I am a roboticist. I build robots. I develop robotics technology. That's me. That's one of our robots, Charlie. If you follow some of our work, our group built more than 40, 50 different type of shapes and size robots. You probably we're focusing on leg robots, 2 legs, 3 legs, 4 legs, 6 legs, jumping, running robots. By the way, open invitation. If you're in LA, I would love to show you our lab. So come to our lab. Our lab is next door is Disneyland. If you like robotics, our lab is more fun than Disneyland. So open invitation, I'll be happy to show you our lab. If you know, follow our work, when you say Dennis Hong, you probably know Dennis Hong or Romela as a research lab focused on humanoid robots, robots that look like humanoid robots. Yes, that's true. The past 2 decades, we've been focusing on a different shape and size humanoid robots. Let me spend just 1 minute showing you some of the robots that we developed the past 20 years. So this robot is called Darwin OP for research and education. It's a fully open source robot, one of the most widely used robot in the world. This one's called Charlie. It's considered the United States' very first full-size humanoid robot. Thor RD for disaster relief, Sapphire robot, shipboard autonomous firefighting robot for the US Navy, and Thor that uses artificial muscles, if I may say, and many different type of shape and size humanoid robots, many different type of things. So again, I have a dream in the future. I would like to have robots living in my house, doing the dishes, taking out the trash. That would be great. That's my dream. However, making human robots is very, very challenging. So do we really need human robots? The famous architect Louis Sullivan once said, form follows function, which means that the shape of an object is dictated by what it needs to do. So instead of asking why we need human robots, let's think about what kind of task requires the human shape and size. Now, as I mentioned, if robots be useful to be used in this environment that's designed for humans, I believe that we need to have human shape and size robots. Stairs are designed for humans to walk up. Your door handles are designed for humans to open up. So unless robots are human shape and size, we won't be able to navigate this environment designed for humans or use tools designed for humans. Some of our early disaster relief robots, human robots, because if you go to the disaster sites, there's still tools, excavators and shovels, and robots can use those kind of things. So it's really a general purpose Swiss Army knife type of robot. So I am a roboticist. A disclaimer, I am not an expert in AI. However, as robots and AI, we need both. So we are end user of AI. So today I would like to talk about AI for robotics and robotics for AI. Now, AI is a very wide term. The field of reinforcement learning has been used in robotics for many years, and it's been very successful. But these days, if I say AI, for the general public, we're talking about machine learning. Inside the machine learning, we're talking about foundation models like LLM, large language models, or generative AI. I'm sure that you're all familiar with these type of AI, ChatGPT, DALL-E, Sora, these kind of things. ChatGPT, it's an AI chatbot. I'm sure many of you are using it. I also actively use it. It's great for translation or summarizing documents. It's very, very useful. DALL-E, you write a prompt and it generates realistic images. And of course, Sora is similar, but for video. You've seen these kind of things, and now we're all familiar with these type of LLM or foundation models. Okay, that's great. Let's talk about ChatGPT. Now, these are machine learning based AI, which means that to make this model very successful, you need to train it with a vast amount of data. You have to put a lot of data, and only then it starts to be useful. So what type of data are we talking about? Where does the data come from? Now, ChatGPT, what kind of data does it use? It's text, right? It's text. How do you get the text? Textbooks, publications on the internet. Text is vast. We have so much information, data for text. What about DALL-E? These are the images. Where do you get images? We have digital cameras, smartphone cameras, and the internet. We have so many images, so DALL-E, these kind of things are used to train. Similarly, Sora, video, YouTube, we have vast amount of data for video, so these are great. Now, these type of AI lives in your computer, in the cyberspace, in the cloud, but for AI to be really useful in everyday physical tasks, we need embedded AI. And what is that embedded AI? That is robotics. Okay, so let's try to use these LLM or generative AI for robotics. ChatGPT, data was text, DALL-E was images, Sora was video. Then what kind of data would robotics require? Have you thought about that? What kind of data should we use? These are physical moving machines, so we need to have these physical parameters like motion, position, velocity, acceleration. It needs to pick up things, contact, impact, friction. We need these type of robots in order to come up with these foundation models for robotics. But how do you get these robots? Do we have a database of these things? If you search the internet, do you get data for contact information and motion data? We don't. So that's one of the difficulties. So for robots, for AI, these type of foundation model for robotics, we need to figure out how to get this type of data, and there's many different approaches. Like for example, by the way, everything I show you is also very recent, and everything is changing every week. So you're probably familiar with NVIDIA. NVIDIA is leading the field of using simulation. So instead of actually using robots to gather data, let's do it into cyberspace. So this is a simulation environment that lives in the computer. So your robot, these are all simulation. So in the simulation, they can walk, fall, pick up things, and from that we can try to gather data. And use that data, let's train our robotics foundation model. Sounds great. However, it's not a silver bullet. It doesn't solve everything. Now, you probably heard the term sim to real gap, which means that even though the fidelity of the simulation is quite high, still, it's never the same as the real physical parameters. When this robot falls, the impact, friction, yeah, we can sort of model it, but it's never the same as what happens in the real life. And that gap makes a huge difference in actually making the robot a controlling robot. So simulation is doesn't solve everything. Now, another approach is, let's make it learn from human demonstration, from videos. So in this case, this is Tesla. So what they do is, they actually have people wearing this data globes and actually VR headsets or augmented reality headsets. And the humans actually try to mimic the motion or create new motion. And from that, they're trying to train their end-to-end learning model for their Optimus humanoid robot. Yep, sounds reasonable, but we really need vast amounts of data. And can you imagine humans in a almost like a factory setting doing this 24/7? This is also very challenging. Another one is, hey, we need data for robots, so let's just use a robot to gather data. So this is an example from Google. So they actually really use real robots, and while making it do tasks, it actually has sensors, so we gather data to train the model. Sounds great. For manipulation tasks, it's great, but if you want to have robots walking bipedal locomotion, it's not the best because the robot's going to fall and break. So these are some solutions, but none of them are perfect solutions. So with this, today I would like to talk about in our AI for bipedal locomotion, walking with two legs, because that's our current focus. And I would like to use two very, very interesting examples that we developed in our lab. One robot is called Blue. The other one is called Artemis. I'm going to talk about these two robots and using that as an example. So I am very, very excited to show you our latest, greatest robot, Artemis. Artemis is a full-size humanoid robot, and if you do robotics, your jaws are dropping right now. This is one of the most advanced electric-powered bipedal humanoid robot in the world. Artemis stands for Advanced Robotic Technology for Enhanced Mobility and Improved Stability. Every 2 weeks, we bring it outside at the campus, and this is the good panwan, without any safety wires, making it walk outdoors. This is the ultimate thing. So as you can see, this robot is very, very robust. You kick it, you cannot make it fall down. Now from the side is more difficult because if you pull and twist all. Now again, if you look at it, you're not baiting it, really kick it really hard. In this case, of course, 왼쪽 도 키워야 되죠. So we're throwing off. Is that it? Now this is a 5 centimeter tall obstacle. We're not using its vision. It's just doing this based on the foot sensor. This is very impressive. Let's do some randomly placed object. This is a 5 centimeter sponge, and trying to balance and walk on a sponge is very difficult. And Artemis can handle this without any problem. This is also this is the very first robot from academia that can run. When you say run, it means that both feet off the ground and has a flight face. And I believe this is the world's third human robot that can run, but the first one in academia. So this is our laboratory. We're trying to make it go around the hallway about 260 meters and then now returning back to the lab. What you see over here, this is fully autonomous. We're not remote controlling it. But it's based on its stereo cameras trying to figure out how to avoid the obstacle. Now, if you're curious how the robot sees the world, let me show you. This is how Artemis sees the world. Right, so it uses a stereo camera system to figure out the 3D geometry and it tries to figure out how to avoid obstacles. So this is Artemis's AI system for navigation and vision. Now this robot can walk 2.1 meters per second, and this robot is the world's fastest walking robot until 3 weeks ago. Now China came up with a faster robot, but of course next week we're going to beat that record. However, our robot, we believe that it's the world's fastest running robot. We don't have the data because we don't even have enough space in the lab, but we believe that this is the world's fastest running robot. And off the record, you know, the Paris Olympic just ended, right? And then when's the next Olympic? Where? It's going to be LA. You might be seeing Artemis do something in 4 years. Preview. Alright, so let's make it do some useful work. Let's make it carry a box. Now, this box is empty, but we tried it. Yeah, it's fine. So we want to give it a bigger task. This time it's carrying a box larger than itself. By the way, it's real-time balancing while walking. Of course, it cannot see because it's blocking the vision, so let's put it on the head and it works fine. Let's try to pull or push a cart. Now, what's interesting is, for this, we didn't have to create a new behavior because it's so robust. You just make it walk into the cart, just pull it, and everything just works. This is remarkable. We are very proud of our robot, Artemis. Now again, this is 로봇의 끝판왕. It handles the 잔디, gravel, the sand, and transition. It just handles everything. This is one of the most robust bipedal robot, electric-powered bipedal robot in the entire world. And again, you haven't seen anything like this. We just bring it outdoors and we test it. This is absolutely fantastic. So Artemis again stands for Advanced Robotics.